The performer model attention approximation has linear time and space complexity in the input token count or sequence length, in contrast to vanilla transformers square complexity. So today I will be discussing a paper from Google called Rethinking Attention with Performers. It uses kernel approximation to approximate attention matrix by decomposing it into multiplication of two matrices, and using this we can reduce complexity in the sequence length, and we can effectively start doing transformers on longer sequences, for example 4,000 tokens. And this is important for us because the longer sequence, the more context the model can get, and you can work with the more complex text. So this kernel approximation, what is this, right? And well, once more, the complexity is reduced here from the squared in the sequence length to the linear in the sequence length. So that's a big jump, and it's super important. Whenever you try to do something, you need to most of the time have linear complexity. If you are working something that has this huge dimension, and the bigger dimension the better, like the sequence length, then you always try to get it linear. Of course, if the other variables in the linear complexity would be still big, you wouldn't help yourself. But in this case, we can do this. So I previously discussed kernel approximations in case of word movers embeddings, where we are approximating word movers distance with kernels. Word movers distance is basically earth movers distance, but over word embeddings. All right. So there's a page on my blog about this, the things I learned about this approach. So now this kernel approximation is used in the transformers. So how is this done, right? So a little bit of context first. So the attention mechanism is the kingpin of the transformer model. It drives all the results, but it also runs memory and time bracket with the squared complexity in the input token count and the latent representation dimension D. The reformer and longformers attempted to topple the dominance of the original transformer with the complexity L log L in the sequence length, but that's not quite good enough. There was this one model, Linformer, they called him, which had a linear complexity, but it didn't quite make it. The approximation is still not as good. But this new model, Performer, seems to actually be almost as good in terms of a perplexity as a transformer, but is still linear in the sequence length. How does this actually work? So yeah, we have this attention matrix, and that's unfortunately n times L. Every token can be attending any other token. And that's this matrix A is actually a result of softmax on multiplication of queries and keys. So this nonlinear transformation, and then it has to be multiplied with value matrix. And because of this multiplication, we can see that we need to do L multiplications, L times. So we get L squared. So, however, if we could decompose A into a multiplication of two matrices, which we cannot with 100% accuracy, because A is a result of nonlinear transformation, but if we actually could, then we would have some small dimension M in between them. So here on this picture on the right, we have a Q and K. If they are multiplied, they approximate A. So if we could do this, so we would get complexity of LMD, and then multiplied by Q, we would get another plus LMD, so it would be linear in L, and this dimension M, which needs to be small enough. And so this approximation is called favor plus attention, and has a linear approximation. Okay, so the Performer paper suggests a approach using kernels. They approximate this attention matrix, which is calculated from query matrix and key matrix, and softmax on it. They approximate this with kernels. And to just quickly prove that they achieved linear speed, we can have a look at this graph. So here's the model forward, basically model prediction, and both scales both axes are log scaled. And if we have a look, so here's the optimal attention. That's basically attention with doesn't have any softmax. It's completely linear, and we can see it has low overhead, obviously. But what's important that it scales linearly with the sequence length. If you look at the classical transformer, you can see that the dashed the dashed lines, so those dashed lines are curved and they curve upwards. So you can see that squared complexity. However, if you look at the straight lines, which are not crossed, those are performer lines, and then we can see that after overhead becomes insignificant, the performer increases complexity linearly. Okay, so how do we do this? How can we not pay for the attention? So listen on, traveler. I will tell you a great story. So how do we not pay for the attention? Original attention is a value vector weighted by softmax applied to the dot product of key and query matrices. So if we have a look here, it's this, we have this softmax applies to Q times K transposed. We have some scaling, and we have this softmax that's multiplied by value vector. The expensive part is that we cannot decompose losslessly the softmax into two matrices and first multiply with the value matrix and then with the Q matrix somehow. And if we could do this, we would get subsquared complexity. And we can do this with kernels actually, and we can do this with kernels actually quite well. As I mentioned, there's other blog post which you can give you another insight into the kernels. Also, they use very similar kernel approximations. These random features kernel approximations for word movers distance in that case. But here we are approximating the softmax effectively. So in the performer case, the transformer attention is approximated by kernelizing the softmax using positive orthogonal random features. I will try to explain this here. I don't know, have you heard about the orthogonal random features? I will try to explain them. So if we have a look at the softmax, if and jth value in the matrix. So if you have a look at that, we would actually see that means that if we do dot product of two vectors, two rows from one row from Q, one row from K, if you do dot product and apply softmax, we get the value in the attention matrix. And we can have a look at this we can define this as if that's the output value of our kernel, which we will try to approximate with dot product in some higher dimension. That's the trick with the kernels. So if we ignore rescaling, we can look at the softmax as the exponential of the dot product of x and y. We can rewrite this into exponential of sum of squared norms times exponential of norm of x plus y squared. Now in here, this exponential x plus y is usually approximated with the trigonometric functions. So that's there is a well-known approach. Is this? I think is the transformation invariant kernels. I think it's called something like this. There's well-known ways how you can approximate it, and it's usually using trigonometric functions and random vectors. However, in this case, we will use a little bit different approach. Well, in the paper they use different approach, and this approach actually uses hyperbolical functions instead of trigonometrical. But I will mention that later. So this part, this exponential of a norm of x plus y, how it actually becomes, how we can actually approximate this with some kind of random vectors, where the random vectors come from. This can be seen actually quite simply. So we take this value, we multiply it with the integral over standard normal distribution with the mean that's actually placed in the x plus y and random omega. And if we move this value that we had at the beginning under the integral and we do some rearranging, we actually get a mean value of an exponential of omega dot product with x plus y, and this is what we actually wanted, because now if we draw omegas from standard normal distribution and we take an average over the omega over exponential of omega dot product x plus y, we will get our approximation of the softmax. And important part is that we can then, if we know that the approximation is enough, if we draw random vectors, then we can approximate our kernels with a dot product of exponential dot product with the x dot product with exponential of omega dot product with y. And this is the it's a dot product from which in the full dimensionality we will get the matrix multiplication here at the beginning. So we will decompose A into Q prime, K prime, where these Q prime and K prime are a result of nonlinear transformation. And we will reduce the complexity by firstly multiplying value with this K, where the M here is the small. Those are the random vectors. These M or R are actually, those are, in the paper they often use M, R independently for the same value. Alright, so where do they get this hyperbolic cosine, these hyperbolic functions? So there's a neat little trick. They use the isotropy, the distribution, and if they actually rewrite this exponential dot product with u, it's easy to use the isotropy of the distribution to get the cosinus. And if they use this cosinus, they actually get better approximation with the less vectors. That's what we want to get. And they call this mechanism favor, but sorry, I'm actually mistaken. There's one more thing in the approximation that helps to reduce the number of random vectors or random features. And so how do we improve on this? There's this mechanism of drawing random vectors. Can we somehow draw them better and not just completely random? Yes, we can. So we will draw them orthogonal, but to still have a little bit, to still converge into the standard normal distribution. How can this be done? Well, if I understand correctly, they basically draw each value of each vector independently, randomly. With this, they will get the isotropical distribution. Well, not exactly isotropical just yet, but if you normalize it, you would get isotropical, I hope. And there's this one more thing. Once they have this vector, they will add it to the set of vectors they already created. But first, they will remove all the projections to the vectors they already have, and from this they will get orthogonal vector to the previous one. So they are getting orthogonal vectors. But a moment, the norms obviously will not match how to get correct norms. So if I understand correctly, they then draw for each vector a norm from Maxwell-Boltzmann distribution, and as a result they will get orthogonal vectors which are randomly drawn from standard normal distribution. This draw converges to random normal distribution. Why orthogonal vectors? Because if you sample in this way, you sort of cover faster the possible dimensions, and you need less random features to approximate this distribution with average. And why the average, right? So as I mentioned, average is basically a sum, and once we have a sum, we will get the dot product, and from the dot product the matrix multiplication will come about. And once we decompose in the matrix into matrix multiplication, we will get the speed up. So what kind of numbers of vectors? So for very long sequences, 4000k input tokens, which is contrast to classical transformer of basically 512. For these very long sequences, we need the m of only 256 features. So this dimension m or r m here, yes. So this one is only 256. Okay, so we will get the speed up, but can we outperform other models? In the paper they mention Linformer and Reformer, and they show they outperform them. So this Linformer, it approximates all these matrices Q, K, and V with the lower dimensional projection. And if I understand correctly, this lower dimensional projection is trained. And they make the right assumption that they can that the matrix A is low dimensional. Well, it's very sparse because most values are very small, and thus there should be some way how to sparsify those matrices and compute less values, and thus reduce the matrix multiplication complexity to just linear in input token count. Okay, but this approach is a little bit worse than when using performer. And we can see it on this graph. So if we compare Linformer, which is the red, with the performer, this blue, we can see already that the performer does a little bit better. But okay, what are these redraws in the graph? So what they here explain is that you don't have to stick with the random vectors you've selected, and the Linformer does also this parsification. It has an element of randomness in it, and there's element of randomness in it. And so if you from time to time redraw these random vectors, you will get better approximation. So performer is a little bit better than Linformer in terms of perplexity, but if you allow redrawing as you did for Linformer, the performer has this second rapid descent, which gives you in the end perplexity very similar to the original transformer in contrast to the Linformer. So performer outperforms Linformer. Performer over Reformer as well. Well, Reformer approximates attention with locality sensitive hashing. It again makes the assumption that the attention matrix is very sparse. Most of the values are zeros, and that's most of the values are zeros. So what they do there is they use hashing function to discover which dot product will be zero or which products will be non-zeros. And they use the hashing. So they take all the vectors together, which they will need to multiply to generate attention matrix. And they first do a very quick calculation of which ones can have zero dot product and which one not, and which one can have non-zero dot product. They shall calculate their dot product. So the complexity is non-linear. It's L log L for reformer. So performer has not only lower complexity, but actually from the graph in the performer paper, it also outperforms reformer. And if you have a look at this graph, you will see that the performer actually for the same amount of layers outperforms reformer on ImageNet 64 task, which is basically language modeling on images. That's one of these new approaches. It's sort of funny, but yeah, interesting new approach. And the metrics are bits per dimension, which is sort of like log likelihood, and steps, number of steps. Okay, so that's all. I hope you liked it. I hope you get at least sort of the juice, the idea, the spice of the paper. And if you like it, subscribe for more, and see you next time.